The final type of problem to talk about in this section is distance problems. In order to solve distance problems, you need to apply a formula, and that formula, the distance formula, is rate times the time is equal to the distance. Because that formula always works for distance, many people set up a chart, very similar to the charts that we were doing with the mixture problems, in order to do the distance problems. The chart is once again really three different columns, and it is the rate multiplied by the time is equal to the distance. The only thing that you need is you do need headings for each one of the rows so you know what it is you are talking about. And you will see that in the next slide as we start doing the first problem. Here's the first example. Two trains, 276 miles apart, start towards each other on parallel tracks. One train travels 8 miles per hour faster than the other. If they meet in 3 hours, find the speed of each. So I'm going to set up a chart that shows the formula in order to solve it. So as I go through and set up my chart, once again I am going to have these three different columns. But this time I am going to have the rate multiplied by the time is equal to the distance. I have two different trains here, so I am going to say that the first row is going to talk about the first train and the second row is going to talk about the second train. And now I'm just going to start to take information from the problem and put it into the chart. It says in the problem that one train travels 8 miles per hour faster than the other. It doesn't really matter which one I want to have travel faster. I'm going to say that the first train is traveling at a rate of X miles per hour. I don't know what it is. And if the second train is traveling 8 miles per hour faster, it must be going at a rate of X plus 8. It says that they were starting towards each other and they meet in 3 hours. That must mean that their time is exactly the same. So their time is 3 for both of those rows. Now I'm just going to multiply the rate times the time to get the distance. So in the first row, the distance is 3x. In the second row, the distance is 3 times x plus 8. So now I need to come up with my equation. The two trains are 276 miles apart, and they are going to meet in 3 hours. That means that they are going to go a total between the two of them of 276 miles. So my equation is just 3x plus 3 times x plus 8 in parentheses has to equal the total distance that they traveled together, which is 276. Solving this quickly, I get 3x plus 24 is equal to 276. 6x plus 24 is equal to 276. If I subtract 24 from both sides, I get 6x is equal to 252, which means, when I do the math, that x is equal to 42. That means that the first train must have traveled 42 miles per hour, and remember, it asked me to find the speed of each one. If the first one traveled at 42 miles per hour, the second train must travel 8 miles per hour faster than that, or 50 miles per hour. So that's the answer to this particular problem. When doing distance problems, you are sometimes given a total distance that different objects go together, or are sometimes told how their distances compare to each other. Regardless, the equation rate times time equals distance always works. Here's another example. Tom leaves Los Angeles at 8 a.m. and drives north at an average speed of 50 miles per hour. Jerry leaves Los Angeles at 8:30 a.m. and drives north on the same highway at an average speed of 60 miles per hour. At what time will Jerry overtake Tom? Once again, as I go through and do this particular problem, I am going to set up my chart. My chart looks exactly the same. It is the rate times the time, times the time is equal to the distance. And I have two different people that are traveling here. I have Tom, so that's going to be my label for my very first row, and I have Jerry. It says in the problem that Tom leaves and drives north at an average speed of 50 miles per hour. So I'm going to put that into the chart. Jerry leaves and drives north at an average speed of 60 miles per hour. As far as the time goes, I don't know how much time. That's what the question is. So if I say that Tom's time is X, I need to now figure out what Jerry's time is in terms of X. It said that Tom left Los Angeles at 8 a.m. and Jerry leaves Los Angeles at 8:30 a.m. That means that the time that Jerry is going to be on the road is going to be a half hour less than the amount of time that Tom is on the road. So in this particular case, I need X subtract 0.5 for 1/2 of an hour, because he's going to be on the road for 1/2 hour less. Once again, I'm always going to get the distance by multiplying the rate times the time. So it's 50x for the first row and 60 times x minus 0.5 for the second row. Now I need to come up with the equation. In the question it says, at what time will Jerry overtake Tom? Well, if they both left Los Angeles at the same spot, when Jerry overtakes Tom, isn't it true that they would have traveled the same distance? For that reason, then, I am going to let their distances be equal to each other, and that's going to be my equation. So I have 50x equals 60 times x minus 0.5, and then I'm going to go through and solve that. If I go through and solve that, I get 50x equals 60x minus 30. If I subtract 60x from both sides, I get negative 10x is equal to negative 30, which must mean that x is equal to 3. Now make sure that you do go through and you answer the question. The question in the problem said, at what time will Jerry overtake Tom? You can't give me an answer of 3. 3 is how long Tom was on the road. And if Tom left at 8 a.m., that must mean that at 11 a.m. is the spot where Jerry would overtake Tom. So the answer to this particular problem is 11 a.m. Here's a problem for you to try first on your own, before watching me solve it. Two cyclists head in opposite directions from the same point at the same time on a straight road. One cycles at 10 miles per hour and the other at 15 miles per hour. In how many hours will they be 75 miles apart? I'll let you go through and set up a chart in order to solve this. Please pause this while you're doing that, and then start it back up again. This is how I would go through and solve this particular problem using a chart. First of all, I'm going to go through and set up my chart with my different column headings of rate times time is equal to the distance. And I'm also going to have my labels for my different rows. I have two different cyclists. I'm just going to call them the first cyclist and the second cyclist, and then I'm going to start to put the information in the chart. It says that the first cyclist, or one of the cyclists, travels at 10 miles per hour. So I'm going to put that in. And the second one, the rate is 15 miles per hour. According to the problem, they both started from the same point at the same time. And I want to know in how many hours will they be 75 miles apart. That must mean that the time that they're both going to be on the road would be exactly the same, because they started at the same time. Once again, I'm always going to be multiplying the rate times the time to get the distance. So my first row, I get 10x for the distance. For my second row, I get 15x for the distance. The question says, in how many hours will they be 75 miles apart? So the total distance that they are going to travel together between the two of them would be 75. So my equation would be 10x plus 15x is equal to 75. and then I would just go through and solve that. 25x is equal to 75, so x is equal to 3. So that must mean that 3 hours after they start going at those speeds, they will be 75 miles apart. Once again, there are all sorts of practice problems you can find in this module on distance problems. As always, please ask me for extra help as needed.